Hi guys, and welcome to our Wadix Technologies YouTube channel. Wadix Technologies is a company specialized in embedded systems technologies. We offer wide varieties of YouTube videos, free blogs, articles and tutorials on embedded systems, as well as wide varieties of online courses specialized on embedded systems. Feel free to check out all of this in our website wadixtech.com. So welcome to today's video. In today's video, we're gonna learn the ARMv8-M TrustZone. First of all, we'll go through the TrustZone concept itself to understand how ARM was able to bring security into embedded systems via this TrustZone topology. Then we're gonna see how ARM was able to implement this embedded security TrustZone on their ARMv8-M architecture, and how those hardware modules like the security attribution unit and the implementation defined attribution unit are used to split our software and addressing space between secure and non-secure domain. Then we will demonstrate how we'll be able to trigger a security state transition on ARMv8-M based architecture. Means how we'll be able to switch back and forth between secure and non-secure state. And here we are not speaking up about the theory part only. We'll demonstrate this security state transition with a live demo to be executed on an LPC55S69 microcontroller. The ARM TrustZone consists mainly of splitting our embedded system application between a trusted software entity and non-trusted one. The trusted software entity will be the software that will have full access to the critical areas within our microcontroller, as well as secret data. And secret data will include, of course, the secret encryption key as an example. The non-trusted software entity will be mainly the user application, and this one should not have access to any secret data or critical hardware resources. So the main idea behind this ARM TrustZone is to create kind of hardware isolation between the non-trusted software and the trusted one. Now, to ensure this isolation, the trusted software entity will run in secure domain, and the non-trusted one will be executed in non-secure domain. Secure domain means the CPU should run in secure state, and the hardware resources that the CPU is trying to access are marked as secure. So we'll have a security state assigned to our CPU, as well as security state attribute assigned to our hardware resources and address space. Similar to this, when running in non-secure domain, then the CPU should run in non-secure state, and the hardware resources and address space should be marked with non-secure attribute. With this, we can create isolation in terms of hardware as well as logical accesses between the secure area and the non-secure one. the implementation of this ARM TrustZone concept was not done initially on ARMv8-M architecture. Actually, when ARM started implementing this TrustZone, they started with the application processor's Cortex-A. So this was done initially with the ARMv7A, and then they moved it to the ARMv8A. However, those processors are application one, and ARM had to migrate and integrate this TrustZone into low power based microprocessors. And to be more precise, they have integrated this TrustZone into the Cortex-M microprocessors. Hence, the ARMv8-M architecture was the first low power based architecture that has implemented this ARM TrustZone. Now, as you can see in this diagram, although the TrustZone here in terms of concept is similar between the ARMv8A and the ARMv8-M, however, the implementation is quite different. Now, in terms of concept, we need to have two domains, secure and non-secure. And this topology or idea has been kept between the ARMv8A and ARMv8-M. So the trusted software will run in secure state, means it will be executed while the CPU is running in secure state. And the non-trusted software or the user application will be executed while the CPU is running in non-secure state. Similar to ARMv8A, on ARMv8-M, the trusted software will be executed while the CPU in secure state, and the non-trusted one will be executed while the CPU is in non-secure state. Nevertheless, the switch back and forth between secure and non-secure state is quite different between the Cortex-A and Cortex-M. In Cortex-A, we need to move through this intermediate mode. Here, the secure monitor software will be executed in exception level number 3. This one will be always in secure state. Now the top level application or software, they're gonna execute either in exception level 0 secure or exception level 0 non-secure, as well as exception level 1 secure and exception level 1 non-secure. Exception level 2, this will be always in non-secure. Now, as you can see here, the exception level 0 and 1, they can be either insecure or non-secure. Now, the way to switch between exception level 0 secure and exception level 0 non-secure, same here for exception level 1, is via the exception level 3. It means we need first of all to jump to exception level 3 that will be running insecure. Then this one will access certain control register, and in this control register we'll have a magic bit, this non-secure bit. If this bit is set to 1, then the CPU will execute in non-secure. And if it is cleared to 0, then the CPU will be running insecure. This state transition will not impact the exception level number 3. this one is always fixed to secure. However, it will impact the state of the CPU while running in exception level 0 or 1. Hence, if we jump from exception level 0 secure to the exception level 3, then we set this bit to 1, then we return back to exception level 0. This time the CPU will be in non-secure state, and hence will be executing in exception level 0 non-secure. Same approach and same flow is applicable for exception level number 1. We switch first to the exception level 3. We have this secure monitor software that will manipulate this non-secure bit, and if we want to switch to exception level non-secure, we set the NS bit to 1, then we return to exception level 1, but this time the CPU will be running in non-secure state. So as you can see, the flow of security transition is done via this intermediate mode. Of course, this will involve a huge overhead due to the backup and restore of the CPU state once we are switching back and forth between the different exception levels. However, this overhead is totally acceptable if we are running in Cortex-A. Here, the Cortex-A is running in terms of gigahertz, and hence we can compensate this additional overhead that is included once we are switching back and forth between the different exception levels to switch the CPU security state. If we try to integrate the same flow into Cortex-M, then we'll have a big problem, because the Cortex-M is running in terms of megahertz, not gigahertz. And hence, this overhead, if we are trying to switch the CPU state when moving back and forth through this intermediate mode, will be, will have big impact on our execution on ARMv8-M. And hence, this will slow down the performance or overall performance results and numbers of our embedded software, and of course will have an impact on the deterministic behavior of our Cortex-M microprocessor. Therefore, ARM has to change the flow of switching between secure and non-secure states on ARMv8-M architecture. And this state transition will be address-based state transition. Means, if we are running a secure application while the CPU is in secure state, and then we want to switch to non-secure one, then we should execute set of instructions, and the destination address should be marked as non-secure. Those set of instructions to be executed are newly added to the ARMv8-M to trigger the CPU to properly switch the state. So we should execute those new instructions, plus we should have the destination address marked as non-secure. Similar if we want to switch from non-secure to secure. So the tagging or the attribute of the destination address will have an impact on the CPU state, whether to be secure or non-secure. Hence, we are minimizing this backup and restore routine needed in case we want to switch via an intermediate mode. So this will not be the case on ARMv8-M architecture. If there is something we need to keep in mind, is that the security state of our CPU within an ARMv8-M based architecture is defined by the destination address that we are jumping to. This means that the security attribution assigned to this address will play a big role to define the security state of our CPU to be secure and non secure. This means if we execute the proper instructions to jump back and forth between the different security states, and then the destination address has the proper security attribution assignment, then the CPU will be able to switch safely between the different states, secure and non-secure one. Now, if we try to compare the ARMv8-M architecture to previous one like the ARMv7-M, we can see that on ARMv7-M we had the support only of two modes, handler mode and thread mode. Handler mode use it as default mode to execute interrupts and exceptions, RQs. However, the thread mode will be the default one to be used while running the user applications. Now, if we move to the ARMv8-M, we'll have, of course, the introduction of this TrustZone. This helps to define extra context or execution context for our embedded software. Here, we'll have the non-secure handler mode, then non-secure thread mode, then secure handler mode, and finally secure thread mode. So we are talking about 4 execution contexts. And this means we can split out our embedded software application into 4 parts. Now, the security attribution assignment to the different addresses within our system is done via those 2 blocks, security attribution unit and implementation defined attribution unit. We need first of all to distinguish between the security state of our processor and the security attribution assigned to our address space. The CPU here on ARMv8-M based architecture can execute in secure state or non-secure state. However, address space can be marked as secure, non-secure, or non-secure callable, and sometimes can be left without any configuration. The security attribution assignment for our address space is defining the access permissions and restrictions. Means there are certain rules to define if the CPU will be able to access a memory region marked as secure or non-secure callable. In general, if the CPU is insecure, then it will be able to access memory region marked as secure. If the CPU is in non-secure state, then it will be able to access memory region marked as non-secure. However, it cannot access memory region marked as secure. And finally, for the non-secure callable region, if the CPU is running in secure state, then it should be able to access this region. However, if the CPU is running in non-secure state, then it can execute only a single instruction out of this memory region. And this instruction that it can execute is secure gate. This region actually is playing the role of a bridge to switch from non-secure to secure. Now, the assignment of these attributions to the different addresses is done via those 2 blocks, implementation defined attribution unit and security attribution unit. So the address to access must be checked first of all against the SIU and IDAU configurations. the implementation defined attribution unit is kind of hard-coded based informations. Means the marking of those addresses to be secure, non-secure, or non-secure callable is hard-coded and saved within this IDAU responder. And hence, during execution, the address to access will be forwarded to this IDAU interface, and this one will try to communicate with this IDAU responder to get the information if this address is marked as secure, non-secure, non-secure callable, or not configured at all, exempt. Then, based on those rules and the state of the CPU, we can determine if the CPU will be able to access that address or not. And if not, then the CPU will trigger a secure fault. Those blocks are not accessible by the users at runtime, so they are hard-coded at hardware level. However, to expose to the user the ability to configure regions to be secure, non-secure, or non-secure callable, then we have this SAU block. This one contains certain mapped registers that the developer can access. Of course, there are certain limitations when using this SAU. If we have an overlapping regions or address space between the SAU and IDAU, then the SAU can overwrite the IDAU configuration only if the region is marked as non-secure or non-secure callable. For the case of non-secure, then it can override that configuration to be secure or non-secure callable. However, if the region is marked as non-secure callable with our IDAU, then it can overwrite it to be secure only. If the region is marked as secure by our IDAU, then there is no way to reconfigure this. So the SAU is forbidden from overwriting a region marked as secure by our IDAU. So as you can see, there are certain rules and restrictions, and those rules and restrictions will be translated to certain hardware logic that is needed actually to determine the end result in terms of security attribution assigned to our address. And this one will play a big role to determine if the CPU is allowed to access this address or not. And if not, then of course the CPU will escalate this to a secure fault. Now, this block diagram illustrates the security state transition on an ARMv8-M based architecture with the support of TrustZone. If the CPU is running in secure state, and then we want to switch to the non-secure one, we can execute this branch with link and exchange to non-secure instruction. This instruction has been newly added to the ARMv8-M architecture, and this one is quite similar to normal branch instruction. Means we are branching to a destination address. Nevertheless, what is new about this one is that the destination address that we are branching to must be marked with non-secure attribute, and the bit number 0 of this destination address must be cleared. By default, if we are executing a normal branch with link and exchange, the destination address must have bit 0 set to 1, and this is due to some thumb encoding restrictions and limitations. However, when we execute this branch with link and exchange to non-secure, then we must have the bit number 0 clear to 0. This is a way to tell the processor we are actually trying to trigger a security state transition from secure to non-secure, and our destination address is located in non-secure region. Now if we meet those two conditions, then this branch with link and exchange to non-secure instruction will be able to jump properly to this non-secure area and start executing from there, and the CPU will be able to switch its state from secure to non-secure. Now to jump back from non-secure to secure, we need to execute this branch with exchange to this function return magic value. A side effect of executing this jump from secure to non-secure using this BLXNS instruction, the link register will be updated with this magic value. And this magic value is newly added as well to the ARMv8-M architecture. And once we execute branch with exchange to this value, the processor will know that we are trying to return from non-secure to secure. And hence, it will restore back the secure state, and it will restore the return secure address. And hence, it will know the location that it should jump to after executing this branch with exchange to function return. BLXNS and branch with exchange to this magic value must be executed in kind of pair combination. Means if we jump from secure to non-secure using the BLXNS, then to return from non-secure to secure, we should execute branch with exchange to this function return. Now, if we are already in non-secure, then we want to trigger multiple jump back and forth from non-secure to secure, then back from secure to non-secure. We can execute this branch with link to secure gate call. Means here we'll branch with link to an entry function, and this function will be located in a memory region that is marked as non-secure callable region. Now the first instruction to be executed must be secure gate. So if we jump to an address located in a memory region that is marked as non-secure callable, then the first instruction that we execute there is secure gate. The CPU will switch right away to secure. If we try to execute any other instruction rather than secure gate from this non-secure callable region, the CPU will escalate it to secure fault. Once we are in secure state, we can return back to our non-secure state by executing this branch with exchange to non-secure. This instruction is quite similar to this BLXNS. Means the destination address that we are jumping to must be marked as non-secure attribute and must have bit 0 cleared. So same conditions as our BLXNS one. However, the major difference is that this BLXNS will be executed in combination with this BX2 function return. But this BXNS is executed in combination with this branch with link to secure gate. So guys, this is our LPC55S69 microcontroller. This one has dual Cortex-M33 microprocessors. One of those Cortex-M33 has already the support of this TrustZone. And this one will be used basically to demonstrate and illustrate the security state transition from secure to non-secure, then back from non-secure to secure. For debugging, I'm gonna use basically an external J-Link probe, as you can see, and this one must be connected to the 10 pins connectors. And of course, I need to power on my port, and this is why I am having a USB connection to my laptop. Now, to demonstrate and illustrate our security state transition with the ARMv8-M based architecture, I have prepared two projects to be executed and run on an LPC55S69 microcontroller. This microcontroller has the support of dual Cortex-M33 microprocessors. One of those has already the support of TrustZone. So our projects will be executed by the one that does support the TrustZone. Now both projects are Makefile-based ones, as you can see. The compiler to be used is the ARMclang. The ARMclang has already the support of the ARMv8-M based architecture. For loading the binary and debugging, I'm gonna use Keil Microvision. Now this non-secure image is the one to be executed while the CPU is running in non-secure state. And this secure image is the one to be executed while running in secure state. And the flow will be like, I will trigger a switch from secure to non-secure, then we'll return back from non-secure to secure. So this will be debugged at C level as well as assembly level. First of all, I will need to start building my non-secure image. So for that, I can just invoke make all, and here we go. So we'll have a build directory that has been created, and we'll have basically our non-secure image to be loaded into our non-secure area. Similar to that, I can build my secure image. The only difference is that I need to specify the secure example to be used. And here we go. I will have my secure image available here under this build directory, and this one to be loaded into the secure area. Now, if you want more details about the projects, the source codes, feel free to reach out to us on wadixtech.com. The company website as well as the email is part of this YouTube video description. After building the projects, I will need to load into our flash memory the non-secure image, then the secure one. I have already automated the procedure to load those images into the LPC55S69 flash memories. So this will be part of our makefile, and we'll have a makefile target called download. If I execute this command, then I will have a pre-configured Keil project that will pop up, and this one will load our binary into the non-secure section. After downloading the non-secure one, we can move forward and download the secure image. Same there, we can just invoke make download. This one will open the Keil secure project, and this one will download our secure image into the secure section. And here we go, this has been already downloaded, and we'll have a Keil debug session that is open and ready to be used. Now, as you can see, this is our Keil debug session, and we are debugging right now the secure project. So here we are in main, so we can just single step, and we should jump to our secure example. I will need first of all to go through this source code to explain to you basically what we are trying to achieve here. What I did mainly is I have created 3 non-secure functions. Those ones will be located in the non-secure image. And then I will be trying to jump to those non-secure functions from my secure application. And once I am here, I will try to jump back from those non-secure functions back to our secure example or application. So those non-secure functions are external ones to our secure image. There is important note is that I need to mark like a type def pointer with this non-secure call attribute. This is needed basically to reference a pointer to our non-secure functions. And then this pointer will be used later on as a way to jump to our non-secure function. This attribute will tell the compiler that this pointer type def is mainly used to reference non-secure functions. And hence the compiler will insert the proper backup routine to save the CPU state before jumping to the non-secure domain. And hence, we prevent the leaking of sensitive informations from our processor registers to the non-secure domain. Now, if I jump here, I can see that we are trying to configure the security attribution unit and mark a certain region to be non-secure. If you remember, to properly execute this BLXNS instruction, we need to have the destination address located in a region marked as non-secure. Now, this example is just a demo about that flow. Means here we are trying to jump to the non-secure domain using this BLXNS instruction. Hence, we need to be sure that the destination region is marked as non-secure. For that, we're gonna use the security attribution unit to mark that region as non-secure. The IDAU, or the implementation defined attribution unit, although it is implemented, but it didn't configure all the regions by default. So this destination region that we are trying to jump to is left without any configuration. Hence, we need to enforce the non-secure attribute to this region that we are trying to jump to. Without that, the CPU will not be able to switch the state from secure to non-secure. So here, I'm creating region number 0, specifying the base address. So this is will be my non-secure section, limit, and then this configuration to mark the region as non-secure. And of course, I will need to have a global enablement for our SIU. Once done, we are sure that our destination address is marked as non-secure. Now, we need to create properly the pointer that will allow us to jump to our non-secure function. For that, ARM has provided certain CMSS macros to allow certain those kind of functionalities. So this NSFPTR create will take as input our non-secure function, as you can see. So this is an array that embed 3 non-secure functions, and then this one will be passed. So the number 0 will be passed as input parameter to this NSFPTR create macro. This one will return basically a pointer to our non-secure function. The main idea here is to enforce the bit number 0 to be cleared. So, if you remember, we should have 2 conditions to properly jump from secure to non-secure using this BLXNS instruction. First one is to mark the destination region or address as non-secure. This is done via this code. The second condition is to have bit number 0 cleared. This is to distinguish that this branch is to trigger a CPU security state transition, and this is not a standard thumb encoding based branching. Hence, we need to clear bit number 0, and this is the job of this macro. Then of course, once created, we will check really if this is a valid pointer or not. Valid pointer or not means we are checking here the bit number 0. If it is set, then we'll not be able to pass this if condition and we jump out. If it is cleared, then we are somehow sure that this is a valid pointer and can be used basically to trigger a jump to the non-secure state. So mainly it's checking bit number 0. Now if we move on, we are implementing a second check to be sure that the destination address is really marked as non-secure. So we'll invoke this check address range and we specify the start address that we are checking, the size, and the attribute used to check against it. Here we want to make sure that the destination address is marked as non-secure. If the returned value is not null, means we'll get the same pointer value, then it means that the check is successful, and hence we can jump here and we'll be able to safely jump to our non-secure domain. Before we trigger a jump, we need first of all to watch out on our CPU state. Here, as you can see, the CPU is in secure state. And once we jump to the non-secure domain, we should have our processor switched to the non-secure state. Now, if I observe the assembly part, as you can see here, the processor is trying to do certain, let's say, backup of our secure state. Or this routine is generated by the compiler. and is generated by the compiler due to the fact that we have stated that the destination function will be marked with this attribute, non-secure call. So this is quite important actually to write a proper secure boot. And once we decide to jump from our secure boot to the user application. So we back up, then we try to clear the state of those registers to prevent the leakage of sensitive informations to our non-secure software. And here we go. This is our BLXNS instruction. And the content of the R0 register will be the non-secure address that we're gonna jump to. As you can see, bit 0 is cleared. If we execute, here we go. Our processor has changed the state to non-secure one. And here we are in our non-secure image. This is a basic function. It will return just 1. So we execute. Then we are branching back to the content of the link register. And this link register will contain this magic value, function return. The BLXNS instruction will be always execution in pair combination with this branch with exchange to this magic value. This magic value is ARMv8-M specific and will tell the CPU that we want to switch back from non-secure to secure. Now if we execute it, here we go. This is our secure return address. So after executing branch with exchange to this function return magic value stored within our link register, the CPU will trigger security state transition back from non-secure to secure. Then it will be able to restore back our CPU register's state. And of course, it will be able to restore the secure return address and jump back properly to our secure image. So as you can see, this is the address right after this BLXNS to our non-secure address.